With a delay here. Anyway, there's let's see, one more thing. So there's a book here. It's kind of, this is just a pile of stuff, but hands-on machine learning. This is what they recommend in a paper, and it's kind of like machine learning and artificial intelligence for the complete idiot. It's in if you ever read those books, the complete idiot books are like set up almost like cartoons. And they do this and that. So the book seems to follow that approach. And you can see it's kind of like set up to act like it's easy, but it isn't that easy. So anyway, so this paper, so this group is from, all right, so I tried to get a grant with Goodyear, you know. It turns out they only fund work from this university in Luxembourg, because they have, and Goodyear's a US company. It used to be a Fortune 500, but they fell out of it. So they aren't Fortune 500 anymore. Anyway, they do all their research from their Luxembourg, a lot of it from there, and they only want to fund the school, University of Luxembourg, which is like, I don't know, Cincinnati State, I think, you know, basically, right? So anyway, it's kind of interesting. This group is from that place, the Grand Duchy of Luxembourg's a little, like a one-town country, right? Near Belgium and France, and Germany, it's not between them. Some reason it exists, but maybe Goodyear must have gotten a good tax break to locate their research thing there, because I don't think they have an industry. It's near the industrial part of Germany, but anyway, so this is kind of interesting because it's really simple. So this paper is pretty good to look at. So I just wanted to go through like two papers, you know, and not, I don't really have slides on it, just kind of go through the papers. It seems to be, they're both from this year, they're both 2023. So the area's active, you know, but I think it's in both of them. In fact, all the papers you find on this are going to be like tutorial. So that people are almost like, this is the first paper on machine learning in this field. So we're going to teach you how to do it, which is kind of an odd thing for something that's at this stage, it's been around like 5 years, I guess. So it's not something you should need to learn how to do, but anyway, it's kind of convenient for our purposes that they do that. So what he does is he basically just copies that book, like that, this machine learning. I mean, he references it and he says, like, if you want to do this, you should get this book. You can look at it if you want. And it kind of tells you how to do it. But this stuff is really like, it's basically like the data analytics, the business stuff, without a context, like just learning the subject is pretty much boring, like totally boring, right? Because it's just like, oh, you can have a neural network and like this and that. But unless you see what it is, it doesn't make any sense at all, right? So basically, it's all example driven. Like the only reason you would do this kind of thing is either if you were a math major or something, or if you have a problem and you think it could help with it, right? So anyway, this is a pretty simple problem, like melt instability. It's an industrial problem. Like when you extrude, so when you extrude, you can get the shark skin form, or you can get a melt slip thing going on. Let me zoom this up. Anyway, if you extrude a fiber, if you get too high of an extrusion rate, then you can get gross melt fractures. So it starts to, instead of being a fiber, it's like just shooting out, right? Some kind of curly Q thing. Then you get the shark skin, which is a very fine. So the bulk property of the thing's okay, but the surface is rough. Or if it's a film, these things scatter light, so the film isn't transparent anymore because it's got this kind of rib thing on it. And then shark skin's a special kind of rib that's got a V shape, like it goes up and then down, up and down. You know, so that's like when you feel a shark skin, it's like rough in one direction, not the other, right? So anyway, anyways, this stick slip is like just alternating slip things. So people have measured that, like people have studied that, and they found this paper from 2008 with on data about this kind of thing. These people are from these actually are like from a pretty high power place. So this is the Center for Polymer Research in Europe, this Max Planck Institute, right? It's near kind of Frankfurt. It's where the Main and the Rhine rivers meet. And then afterwards, this woman went to a company in Austria, and the guy that worked on it went to Basel, which is the same as in Cincinnati, the place Lyondell, Basel. So Basel was a BASF shell. They took their polyolefins and combined them. And then Lyondell was a company in Texas, which I think was also two companies. The Lyondell Basel is actually like four companies combined, right? So all the polyolefin businesses. So there was a big research center in Frankfurt, this Basel. Then they have an Italian research center, which was this shell one, I think. Anyway, so they went to that place. So they both gone to an industry to do the same kind of work, like extrusion and looking at the from the top polymer place. So to look at these melt fracture issues, and in doing that, they used this dynamic oscillatory shear. They did it at large amplitude. Usually this is small amplitude oscillatory shear. So that's like the thing where you just see the sonic vibration. Here they go into large amplitude so they can get this melt fracture. And then from the signal from that, they put pressure transducers on it, and then they can measure the frequency. Like in other words, when it's extruding, there's some kind of frequency because it's coming out with a regular pattern. Right, so they can get that frequency from a large amplitude oscillatory shear, and they can get the stress, the peak difference, the pressure difference between kind of the peaks of the fluctuations that are going on. Right, so you can digitize all this information. So that's why this group in Luxembourg liked this, because they had made tables of like what they call intrinsic properties, which isn't like in thermodynamics intrinsic. This is intrinsic means the polymer, like molecular weight distribution, co-monomers, for polyolefins, be like how many branches, short chains or long chain. Short chains you put in to break up the crystallinity, long chain change the rheology significantly. Like one long chain branch per 10,000 carbons increases the viscosity by 65. The long chain is viscosity enhancer, short chain is crystallinity, changes the solid properties. Anyway, so, and then they've come up with a metric of a branching, and then so there's a lot of numbers. And this is a setup where they have, this is not the large amplitude oscillatory shear. This is another thing where they're just running through a die. So they pressurize through a die. They have a pressure transducer at the die head. Then they have three transducers, and they can they have a rapid pickup of this. So you can get this as a function of time. So you can get these curves. These are the three transducers in the die coming out of the extruder, showing this oscillatory thing that's going to lead to shark skin. Right. So basically, they take this data and Fourier transform it and get a peak. Now, you could measure the difference between these and get the frequency, or you could take this and Fourier transform it and get a peak. So they Fourier transform it and get a peak. The frequency of that's the frequency of the oscillation. Right. So they this is plotting the intensity of the Fourier transform spectra. So anyway, somehow they get a peak out of this and they get a number for the frequency of this F. That's the frequency of those oscillations. Sigma P is the I think that's the change, the height of the oscillations, like that's the height, like how strong are the oscillations. And then A percent. What A is. Anyway, they can map out. You can see there's not much coordination to the thing. Anyway, they're using this. So this group in Luxembourg is using their data. They're just going to take their data and then map it, use machine learning. So the question is like, how to use machine learning on something like this, and what can you get out of it? But they've already come to some conclusions. The basic conclusion is that this shark skin depends on having a high molecular weight distribution. Like this MW over MN is the most important number, not the molecular weight. Yeah, and then the second most important number is like the molecular weight. So it's kind of surprising that this polydispersity is more important than the molecular weight. So that's interesting. So that machine learning, they want to try to kind of map that out. So they reproduced their two tables, table one with the samples, and then whether they're branched or not. And they reproduce table two. And the things that are like names, so they want to put this into a computer program. So the names aren't going to cut it. So they say like 1 and 0 for the different kinds of deformations. Right, so you could say, you could take a sample and you could say it could be like 0.5, like it's halfway between shark skin and stick slip. Right, but these are the training things, are going to just have 1s and 0s for that thing. And then for this branching thing, they have to change this descriptor into like a number. They've already done that for them, I guess. Here they have that number, right? So anyway, and then standard pressure deviations. Let's see that they define what these terms are here. Because they are located at a cell sample, standard pressure deviation, and then frequency, and then what is A? A is the thing, and then what is table 2, it says in here something. 1, 2, do you see it? Maximum nonlinear parameter. A. At whatever frequency. So, we don't know what A is. So A is some number that has to do with the other experiment, right? And this is just a redrawing of the shark skin thing and the problems that are coming out. So this is how they get, so they've translated this thing into these numbers. The paper does that translation also. They do some kind of calculation. This guy defines his own number. So in all these things, you want to have a number that goes from 0 to 1, like because the parameters, one's going to be in bar and the other one's going to be in frequency, right? So you can't compare like apples and oranges. So at least they want to say like, what's the maximum frequency, and then so you're gonna have to have a number that's comparable. In other words, if the frequency goes up to 5,000 hertz or something, and the pressure goes to 2 bar, you can't say like which one is more important, right? So you need to have a metric. So the first thing, you have to get everything in terms, like, in other words, they're trying to parameterize everything on comparable terms. There's 2 ways to do it. They call this normalization. So there's 2 common ways that they do this. So one way is you take the minimum value in your value, subtract, and then take over the range, and that gives you a number between 1 and 0, and the range is 0 to 1. Right. So that's one way to do it, and that's called normalization, I guess. And then the other way to do it is called standardization. So you take your number and subtract from the mean, and then divide by the standard deviation. That's going to give you a number of standard deviations that you are away from the mean value. This number can go plus and minus. Right. So depending on how you pick, so what you're gonna end up with is that you want to take a huge number of things that you measure in an experiment, and then reduce those down to the important numbers, hopefully like 2. So you can do an XY plot and put all your samples on that plot, and then hope that they form clusters. And you can identify like shark skin and stick slip of those 2 clusters, and you might identify like some other groups. So it's basically a data analysis method. And it's all right. So you can see like this is a simple set of data. So they've already done and they've already figured out just by looking at the data. But if you had a huge number of data, like from the computer program, that's spitting out data all the time, And then you wanted to see like what kind of categories of stuff do I have? And then how am I gonna, so, and how does that fit with the output, like what's important to me, like a transition or something that you're looking at. So that's kind of the general theme of this. This is nice because it's just a simple set of data and it's tangible. You can see shark scan versus stick slip, they're like two different melt failure mechanisms. Right, but anyway, so you're gonna have to, so the idea is you're gonna have like many data points, and then you're gonna somehow reduce the number of data to like a few, right? So there's routines to do that. So there's routines to kind of reduce the data set, the number of data input parameters to the ones that are important to the problem that you're looking at. Let's see. So let's see notes here. Intrinsic, extrinsic. So he's got he wants to relate back to intrinsic parameters, not the extruder. Because the extrinsic parameters be like how fast you run the extruder, the temperature of the extruder, the things that aren't the plastic. Right. So you have the plastic and you have the extruder, and he's separating those two. And he's interested in what features of the polymer that he can change to reduce the appearance of shark skin and melt stick slip mechanism of extrusion. So then in doing this, there's two approaches that you can take. So he repeats that in this paper, but it's from the book, but I think it might be easier to read it in the paper because it's condensed. So if you want the details, maybe more of it's in the book, and then there's references in the book that go back to other things. But so he talks about, you can have two ways. You're trying to sort the numbers you get. First, you have too many numbers. You want to reduce the number of parameters to the important parameters, either by picking the important ones or by like binning the parameters. So you can take, so there's routines, and these are all available on software online. So and it doesn't involve thinking like a model, like you're going to calculate a number from your parameters. It's just generic. So you just take the numbers that you have. So a neural network, you would take the numbers you have and you connect every other number that you have with it. And you'd say, well, there's a weight of that one, and that with this one, and those two would combine to it, then you just have one parameter, right? So you can reduce that way, and then you have this array of weighting functions that weight the relationship between any binary pair. And you can do that at different levels, like at level 1, then level 2. So the things you created with your weighting functions from level 1, then you can have another set of weighting functions. So you can see you can have a lot of parameters. Those are going to be fixed parameters for anything you stick in the extruder. You stick a fish in, you're going to use the same parameters. Stick a polymer in, same parameters. So the weighting function you learn by sticking fish and polymers into the extruder, and they should get to a point where you have the same weighting parameters going in. They come down out of the 20 things that went in, you get 2 numbers out. Then you can plot X and Y and see how the data groups according to those 2 numbers that are meaningless, right? And then you have the weighting parameters. So you can take the 2 numbers and then you can recreate. This is how you test your weightings. You take that and go back in reverse and like recreate the thing that you had to start with, which was your original data set. And you do that iteratively until you get the weighting function right. So you have like a fingerprint for whatever it is you're looking at. And you can shove anything in the extruder, get the 2 numbers, map it out, and say there's going to be a shark skin or a stick slip, because it's going to go into one of the 2 groups in your map that you get out of the thing. That's kind of one approach to this. So there's several different approaches. So the first thing, like the numbers you feed in, they have to be 0 to 1 because you can't compare frequency and pressure. Like they're going to be on different scales and whatever. So basically, you can either do it by this normalization, or you can do it by the standardization. So you can see that this, like if you just look at this bare, like if you just pick up that book, this is going to look stupid. Like you won't be able to figure out what's going on, right? But if you have the stick slip thing, you have the data, you can see like you have to do this because you can't compare pressure and frequency. They're going to be on different scales. So you need to pick one of these 2. So he tries both. He tries pick every paper on this, tries every method until they find one that works for them. So the approach is to start with the data set, arbitrary data set, go through every possible method, including standardization, and find out the one that works with your system, and then use that, right? So, so this is just saying to select the features. So this, in this case, all right, so there's two ways you can do: supervised or unsupervised. The supervised means that you know what is it? The supervised would be like, we have shark skin and we have stick slip. There's two kinds of melt failure. One is like a large scale called stick slip, and there's shark skin, which is very fine. You can't really see it. Anyway, so supervised would be like, I know I have shark skin and stick slip, and I'm going to bin all my data into those two categories, and that's what answer I want to get. Unsupervised means I'm just going to see where the data bins on its own, and then I'm going to later on identify the bins with whatever it is I'm interested in. In unsupervised, you can discover new bins. Like you could say, well, all these are in shark skin, all these in stick slip, but there's a group over here that's something else. And then you can go back and say, like, what is that something else? You know, it could be like it makes a curly Q thing or something, right? So anyway, so that's kind of one approach to this. He uses unsupervised. In fact, everybody uses unsupervised because they're trying to discover a new thing. You'd use supervised if your boss told you to do something, right? Like supervised is really like, he wants to know if that thing's, what do you do to make it not show a shark skin? You know, so then you'd use supervised. Unsupervised is if you're, yeah, supervised is quicker. Yeah, it's simpler. But unsupervised gives you this opportunity to discover new things. So that's everyone that's doing research can do unsupervised because they want to see like what the new thing is. So under supervised, there's like regression, which means you're going to get your X, Y, and you're going to fit it to a straight line. You're going to fit it to a polynomial or some Gaussian thing or something. Right. And then the other is that you do classification. So you can see, like in this case, you could classify shark skin or stick slip, or you could somehow get a parameter. So he's parameterized shark skin and stick slip, the instability, you parameterize it with a number somewhere here. And then that number, so you could do a fit to that with a function. You could do a regression with it, do least squares fit into that. And then that's if you have a target that you're going for. If you don't have a target, then you do this thing I was talking about, dimensionality reduction, so reduce down to two unknown things. You say I have 20,000, I'm going to reduce it to 5,000 by finding these weighting functions. And then finally I'm going to get two. And then those two, that's a dimensionality reduction. And the other thing is clustering. Like you say, the 20,000 can be clustered. The things inputs I can cluster into just different things that are kind of, I can write a function with those different groupings of things, and then reduce the number of input parameters that way. What else do I have here? Let's see. And then the text has to be changed into numbers, and these two things to get the scales right. And then feature selection. So yeah, he kind of describes this here. So this is the feature selection thing, right? So he's saying so you can pick your features and then have your learning algorithm. That'll be like getting your weighting functions and going back, and then you can change your set of features that you're using if this doesn't work out. So you have kind of a test routine where you're adopting it for that, or you could take the final result of the system and change the input parameters that you're selecting for it. This is the methods, like 3 methods to select what parameters from all the parameters that you have, what parameters you'd want to use to do your XY plot. Right. So if you're not doing the reduction in the parameters, and you just want to pick the important parameters, you have to decide what the important parameters are. That's kind of the idea. But you want to get to an XY plot if you can. Let's see. remove redundancy, reduce measurements, faster training, and then rank the features. That's what I have here. Before you do the training of the algorithm to figure out how things are going to group. That's the 3 feature selection methods. Anyway, so what else is in here? This is just, so this is kind of from that book. So there's a book here, Hands-on Machine Learning, whatever, that he's kind of taken it from that to get to this thing. So anyway, these are things that are kind of from the book. So like you've identified 2 groups, but there's this other group in the middle, before and after clustering. So you kind of can find things, unknown things. Let's see. So what else is here? Oh. All right. So then you finally get to the point where you have your XY parameters. And then you want to say, like, what is a cluster? That's what this thing is. So so the idea here is that you're going to have, somehow you're going to have an XY. It could be other than like XYZ or something, but basically you pick some size R. These are going to be 0 to 1. Like because you've done these routines, X and Y are both 0 to 1. These things will end up giving you something like 0 to 1, especially the first one, this normalization thing has to be 0 to 1. So anyway, so XY is 0 to 1. You want to define what is a cluster. So you just say R. It's going to be some number between 0 and 1. That's going to be a distance I'm considering. Then you're going to randomly place dots in this sample. And then within that circle, say, where's the center of mass? Then you're going to kind of move the circle in that direction towards the center of mass until it'll hone in on the densest place. And that's a cluster, right, of size R. And then you can look at that as a function of R. That's one way to do it. That's called the K. That's this K means clusters thing. And then shift. Oh, this is mean shift cluster. It's K cluster. I don't remember what it doesn't exactly say what K mean clustering was here. The mean shift clustering is kind of clear. Gaussian is just instead of a circle of R, you give it a Gaussian function weighting. So you give, like, things that are further away, you weight less, and ones that are closer, but it doesn't have a strict cutoff. And then there's these things where the clusters might not be circular, they might be shaped like that. So there's methods to kind of deal with that. This DB scan doesn't really describe that. It's described in that book, right? So anyway, identifying the clusters is a whole nother thing going on. And then basically he gives us an algorithm for what he's doing. So transform the available data into a reasonable format. These has to be numbers 0 to 1. In all the text things like short chain branching, long chain branching, you convert to numbers. And then apply normalization, standardization makes it 0 to 1. Use a variety of clustering algorithms to compare the results. So this is actually after you reduce the dimensions. So, and then you're going to be clustering on XY to try to find out what the clusters are. And then so you train it on a part of the data set that you're going to have as known, like, this is sharp scan, that's, then you're going to go back and test it on an unknown, see if it sorts it right. And then you're going to go back and test, like, then you're going to actually use it to predict, like, what the properties are that you want to get from the thing. Right, so that's kind of what's going on here. So this is that frequency versus molecular weight, and he finds there's a grouping here. there's different ways to plot that. So the blue are shark skin, the red are stick slip, and they, by looking at frequency reduced to 0 to 1, and molecular weight reduced 0 to 1, or 0 to 1.2. I'm not sure how that worked, but he finds these groupings, right? So this is like a looser thing, and it looks like these two are a group. So he says that in here, that like there could be some different phenomena going on for those three than those two. And then you test it with data, right, and see how it matches up. So he tries a standardization method and a normalization method. This is the x minus x minimum divided by x max minus x min, and the normalization is like we're using the mean. And then he gives the results a ranking, and then he ranks all the features to how they're deciding whether it's shark skin or whether it's and he finds out that this molecular weight distribution is the strongest correlated with, and then the second is molecular weight, third is frequency. So you see the input parameters are kind of deciding what's happening with the extrusion. Average score from different methods that he went at this. So he's got like, right. So basically he finds out kind of what the other guy found out. This is comparing, so you can see it's like he's doing like an overview of all the different possible machine learning methods you could use to look at a simple data set. So so it's almost like a review paper in a sense, based on one data set from one paper, not his paper. So it's interesting. I think it's a pretty good paper. It's published in like kind of an odd journal, but I think it's an industrial, I don't know, macromolecular materials and engineering. I guess, I don't know. I've never heard of it before. Maybe it could be, but it's like, and then Goodyear paid for it because they're in Luxembourg. They paid for owning in Luxembourg. Goodyear will only support research in Luxembourg now. But the US company, it's very weird. So anyway, if you go to ask them for money, they say move to Luxembourg. So anyway, that's one paper. So I got two papers. Anyway, any questions on that? I mean, it's kind of a quick overview. If you're interested, like look at this book, it's in the same area, linking, or just read that paper, you know, in a little bit more detail. I think that's the simplest possible paper on the subject. You know, so, right. So anyway, this is the data paper that's posted up there too. And there's this thing that came out this year too. Like, it's kind of simple, kind of complicated. So this is two guys from India, right? So they're doing they're looking at coil to globule transitions. It's kind of more useful in this class, I guess. But and then this is what they want to get out. It's like they get a number 0 to 1 for coil, as number 0 to 1 for globule, and then they plot it as a function of temperature, and they can see there's a transition, and that's the temperature, the transition temperature. The problem is when you look at these things, all you have, so you can do a molecular dynamics simulation using lamps, and you're going to get the chain, and you got to change the energy, change the temperature. At some low temperature, the coils collapse. But all you have is a graphic. You have like a 3D picture of a polymer chain. You can say, well, that one's smaller than that one. But you don't exactly know like where is the transition that happened. So it's a little bit not well defined, like two liquid states. You can't really tell like the difference, right? So from like if you get the bulk sample, you get kind of the density, but you just have one molecule. You know, you're looking at this in dilute condition. So you can get the size. There's other ways to get at this. In fact, they go back and they do their simulations and they calculate the radius of gyration, which would be like the obvious thing to do. And then you could predict the transition from the radius gyration. And the way they say that their method works is they compare the predicted radius gyration with the reference, like the one that came from the simulation. They say like, well, they match, the thing must work. So they're going to do it. They do a neural network. So they're going to take their structure that they have. So in the numbers here, so they have, I think they have three, like a 50, a 400, 100 or something chain. There's 3 different molecular weights. So going to have each point has XYZ, so 3 times the number of things, like 40 times 3 gives you like how many input data points they have. Then they're going to say, well, there's a weighting function, like for every polymer that I can possibly make, there's a weighting function between if I want to reduce it from 40 times 3 to like 5 times 3. And then I could reduce it to 2 times 3, and then just 2. Right? So each step, you want to just slowly do it so you have not too many weighting functions involved. Right? And these are actual results. Like they start with this one, they reduce it to 2 parameters to describe this whole thing. And then they can use the same weighting functions to recreate the same thing. So it seems to kind of work, I guess. You just take them, like each one has XYZ, and you say, well, I'm going to just have like instead of X, so I have 2 points, I have 6 numbers. I'm just going to say I'm just going to have 3 numbers. And I'm going to have a weighting function for X, a weighting function for Y, a weighting function for Z to connect to the other thing. And then those are just, you don't know what they are, you just guess them to start with, random. And then you go through this routine and you compare the beginning and the end until you get those weighting functions right, and then try another structure and try another structure. And try, so it's a learning process. And then finally you learn the weights. It's the same thing that you did with the extrusion. Okay, it's the same exact thing. The method's the same. So to do this, they just use a web page. Like you just download the thing from the web page and they can just do this. Right, so you can put, the computer doesn't know what the data is, it's just a bunch of numbers. Yeah. And you're trying to predict the same numbers by going from umpteen numbers to 2, and then out to the umpteen numbers. Why is this happening? Well, because no one can understand it. Like I said, not that you lose this total detachment from reality. The final 2 numbers you get are totally meaningless. I mean, the alternative, the traditional, is just take this and calculate the radius of gyration. That gives you 1 number. You can't reproduce the structure from it, but basically, it's 1 number. It's a parameter reduction. You can actually get a lot of different numbers. If you wanted to think about the kind of numbers you would calculate from the structure. So you could do it. You could do it. That would be a supervised. Where you said, like, I'm going to get the ratio, and you get like 30 numbers or something. That would be supervised. This is unsupervised. It's a free for all. The advantage of this is that, again, like you can identify things that you didn't anticipate. It didn't depend on the radius of gyration. So you don't know what's out there. So you're going to be categorizing from these 2 parameters. Right? So, and it's good for computer simulation because you can make as many of those molecules as you want, and they're perfect. There's no experimental error or anything involved. So basically, it's really nice for computer simulation where all they have is a picture. They haven't measured like the radius, like scattering, you get radius of gyration or you get the dimension of it or something. But here you just have a picture of it. So you'd have to convert that anyway using some algorithm. And who knows if you're going to get the right parameters from that. Whereas here you just get numbers, you don't know what they are, right? But you can predict clustering. Like you can take those 2 numbers and then predict that. So that's how they're going to do this, is just take those 2 numbers and then map out state variable 2, state variable 1, and then just map out like where this transition happens from those 2 numbers. And then they can kind of backtrack, like where is the transition point where from radius of gyration, maybe you couldn't get that. It's like not as clear cut. No, in order to verify their thing, they compare with the radius of gyration. So this is what they're getting, the prediction, and this is what we calculate from the simulation. Right. And they match up. So they say, like, oh, our thing works, but why didn't they just use the radius of gyration to, but they're trying to do something different, something new. So that's kind of the point here. Because if they had that, then they could always go. I think like if it was multiple tests to get those great points, and now they can go backwards. Yeah, you can if you have these 2 points, and you can just map through these 2 points and produce any structure you want to. Right. Yeah, that's true. So you have a 2 parameter space. So instead of doing another simulation, I just change that number a little bit. This is how the entire world works now. Like when you call up Amazon or whatever, this is what's happening to the data that they get from you. I bought these sneakers, and then that's going to go in and they weight it. Then next time you buy something else, then they figure out, oh, these two numbers, that's what you are, and they can reproduce you from that. So, I mean, everything I think is like that now. Even the automatic driving is kind of taking a lot of input, all these things, saying, did I hit the kid, like, then you can reproduce the thing and say, like, why did that happen or whatever. So everything's like that, so yeah, and you can just in it, because it's just reduced to these 0 to 1 numbers, and then everything becomes the same problem. Like, so you can just use a shareware to do this, right? So it kind of makes sense. I mean, you can see why people are, especially a manager, who doesn't understand what it is you're doing. Like, have no idea what anyone in this place, I'm an MBA from Harvard, and it's like I'm coming into a petrochemical company, and I had a philosophy degree before that. It's like, well, this is perfect for them. Like, you don't need to understand anything. Just like shove in the numbers, and now it comes the answer. So how much they could just ask, how am I going to raise the stock price? And they can give you the answer. Say, like, kick that guy and give that guy a raise, and that's going to work. So yeah, so you can see, yeah, skepticism is going to abound here. But anyway, so he says the same stuff, like supervised, unsupervised, interested, and unsupervised, because they want to discover something. And then coded globule, about that. And then he's using lamps. He just uses, this is just the same thing we kind of looked at before, some kind of spring thing between the beads, and then there's some molecular dynamics code. They have an interaction, 612 potential. They have some kind of thermostat, blah, 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 and they end up spitting out the chain as a function of the temperature using that lamps, the CNDF thing. And then I guess they do more than 3. They do those molecular weights of chains. And then these are the actual pitch. This is the simulated, and that's what comes out of their machine learning process. He says you can predict molecular dynamic trajectories. So you don't have to do more simulations. You can take the few that you have and say, where is it going to go? Like, say this was say you ended your simulation after like $5,000 of computer time, and you didn't have the 10,000 to go the other half. But if you have the time slices for like $500, $1,000, $1,500, then you could use this to predict. You could draw a plot of your 2 parameters and say where it's going to go. Is it going to plateau out? Do I need to go to $20,000, to get the thing? So you can see, like, that could be useful. 2 parameter X, Y, reach a plateau and done. I mean, you can do the same thing with race gyration. But basically, this looks a little bit more sophisticated. Okay, I'm done. And you can reproduce what the structure would be after $20,000. And maybe it's got some degree of confidence in it. So he's like he uses like 50% of the data he generates in simulations to train the thing to get these weights, and then 10% to test it, and then you can predict the other. He has algorithms for how he uses what he has and what he tries to get. So let's see. So what he's trying to get is these curves, like the state variable 2, state variable 1, and these are numbers 0 to 1 that have to do with coil to globule. I guess he gives a generate polymer trajectory. So he does the molecular dynamics at different temperatures, and then he reduces the dimensionality using this weighting function. He calls the 2-point thing the bottleneck layer. the lowest dimension. And then what's he do? He has the two state variables, coil globule. So C1 G0 will be coil, C0 G1, so globule. And then he's going to train his algorithm at the two extremes. So he has like a high temperature and a low temperature where he knows it's coil and he knows it's globule. Right. So at those two extremes, he trains his system, and then he can get numbers other than C is 1, G is 0. Get numbers in between that way. So that's how he can get this plot where he has a sigmoidal shape thing. Right? And then label step 3 considered as a representative. And then he tests it on some that are also state things. And then this deep neural network, which is a thing with all that goes down to 2 parameters. He can predict from that, like what's the state of the thing. He's going to predict those numbers from he's going to feed in then simulations, and then so he figures out like how does he tell, let's see, this loss thing is kind of interesting. It's a entropy number. It's given here somewhere. Here. The loss of the deep neural network, P is the probability, and T is the true value of a label. So in other words, coil 1, globule 0, that would be true. True value would be like 1. It's looking at the coil thing. And then what's the probability of finding that from his data set? And that gives him this loss thing, which is good because the coil globule can only be 1 and 0, so you can't get a slope of it, like how it's changing. But this loss thing is a number, so you can do a derivative of it and then figure out if he's approaching where he wants to be or not. In other words, he wants to know like how many number of epochs means how many slices do you make? Like do you do 5 where you take the weighting, or do you do like 50, or do you do 2? Right. So he's saying that I should do 2 because as he goes down, his loss drops. Then he finds out how many of those, what's the minimum number of epochs he could get to reach his plateau value for the different molecular weights. It seems to be about the same for all of them, something like 3. Right, so three epochs where he's reducing to how many, I don't know how many parameters. That's how he decides how many levels to do the neural network. So these are like everyone's going to do the same thing, no matter what it. Like this is one example, but if you were doing gas prices at the gas station, then it's going to be the same thing. You still have to figure out how many levels to break down the data that you have. And then like gas price would be like, you'd have to rank it 0 to 1, like the maximum, minimum, or whatever. So, and the probability he gets, this is how he calculates a probability. It's basically the same thing. It's a Boltzmann function. The same, like in thermal, we covered that function, right? It's basically, this is the, that's the invariant, not the invariant, what's that thing called? The sum of states, Zusammensumm, what's that thing called? Anyway, this just gives you a probability from thermodynamics. So they're just using like thermodynamic stuff to do this, to get an entropy. And then that's where he proves that. And then this is this is a split scale. So this is a training set and then the test set. So he's saying that it worked. Like the yellow should be coil, which would be 1, and the blue would be globule. So it works. It's a split scale, so you can see the fine tuning here. That this thing's actually pretty close to 1. So that's showing that it works. And then this is what he gets when he looks at different molecular weights, which is kind of interesting. So the main point is that the temperature shifts, the transition temperature shifts with, and all the results are known except for the shape of this thing. So the shape broadens for lower, kind of makes sense. Like it's hard to tell the difference between the two, for one thing. When they're small, when they're larger, it's easier to tell the difference. And so it's a sharper transition in temperature. So that his temperature scale is like the 0 to 1 scale also. I mean, it goes to 3, but basically some odd temperature scale. Anyway, so he does see some new information after doing this. Like to see, he can predict the transition temperature, and then by extrapolating to infinite molecular weight, you can get the theta temperature for this coil globule. even though it's not the theta that we talk about, but it's basically an equivalent theta temperature. This 1 over square root of n dependence is just what you expect for the theta, for the phase separation temperature, the theta temperature for solutions, mixtures. Right, so he gets the same kind of, the first term is the same kind of behavior. He's got an added term. Anyway, so it kind of, there is some information. I mean, it makes a kind of a flimsy argument that there's some new information that came out of the thing, even though the new information he got has already been anticipated by the other measurements. Basically, that's the situation. So I'd say that's one of the better papers of this kind of machine learning stuff that's around. And it just came out like recently. I guess this one's 2021. Sorry. There's one other paper that I didn't really have time to kind of go through, but I'm not even sure where this thing is published because it's in one of those, like Cornell or someplace has like papers published before they're published. And this is on one of those servers. This might be a paper somewhere, but it's basically looking at the same thing, like single polymer nanoparticles is the idea that you can have like a globule and use that as a nanoparticle. So these guys are doing kind of the same thing. They're at the national lab, I think. Rutgers, and I thought one of the people was at, I guess they're all at Rutgers. Anyway, so it's kind of the same thing as what the Indian guys did, but they're using a biomimicry kind of thing. For the same, like this is like a protein from the globule, and this is the polymer. It's almost the same thing as the other paper. So you can see people are kind of looking at this. Anyway, it's just kind of an overview of this stuff, but I'm not an expert in it either. So, and I haven't used it. So, but I think it's not that hard to use. We could, like, if I was still teaching the characterization class, I'd make a lab of this and have you go get the software and use it, you know, on some data set that you got, and see if it's of any value. Or maybe a paper's data set, you know, like the guy did with the extrusion stuff. I think you're going to run into this everywhere you turn. Like everyone is doing this. Like the simulation people are doing it. And then and if you can put it in, it makes it whatever mundane thing you're doing look flashy. Like all of a sudden it's fresh. Well, you're doing shark scan and stick slip, but you're doing machine learning. You know, so all of a sudden, instead of being like shark skin and stick slip, which have been around forever, it sounds like it's a new thing. You know? So I think that's one reason they're looking at it. But so far, it's like all this business about experiments in space, you know. Oh, we're going to do zero gravity and grow peas. You know, it's like, you know, of all the money and billions of dollars they spent, like nothing has come out of it, nothing at all, really, right? So it's just like lip service for something. But this definitely has potential in nuclear war, maybe economic prediction for the stock market.
It would be great for the 10 cat. Like the amount of different variables that we have, and just like too much. There's a lot of like predicting factors that we have to do. So
Yeah.
Sometimes it messes up and there's maybe growth and it doesn't account for it. There's like too many like variable things that have to happen.
Yeah.
There's even certain things that can do that this could probably get pretty close to.
Yeah, it doesn't have to know anything about what you're doing.
Yeah.
That's the nice thing.
It would probably be pretty beneficial.
Yeah, so if you don't know what you're doing, it's like this is the tool for you.
Look, these are the reactions. Make the plan for you.
Yeah.
That's like if I consider to do this, I would do it like.
Yeah, I mean, you have to set it up for what your problem is.
Yeah.
But then you could sell that once you set it up. Like there, so this thing, this is actually, I think it's kind of like a business. If it's not a business, it's a way to make them famous. This Poly is like they just put together from the web stuff. They just put together a package that does this, you know.
Do they just have like servers somewhere?
Yeah, I put the links in the thing. Yeah. So they mention it. These two papers mention those, and that book mentions them too.
That kind of stuff.
Probably the Defense Department needs for that. I don't know. I mean, no, maybe it's a lot of these are like, oh, your first $5,000 are free, and you have to start paying, so they can get a lot of people in the front door.
Yeah, I mean, given it's probably large, but
I mean, it's like Chat GPT, right? And
Yeah.
basically eventually be like, well, I really need this thing to answer all my quiz thing. Are you willing to pay $20 for it? It's like, yes. So, I mean, it's a lot of, they probably have an algorithm running out there, just feed it in. You don't even know what you're doing and just say like, pull this lever. And so,
I just don't know where that, like, if one company really understands AI, like one
Mhm.
company really understands AI,
yeah,
it gives them such a nice spread.
yeah. Well, they're all investing in this stuff.
Yeah.
I mean, I think everyone's put money into it. I don't know for sure. I'm not doing it, but basically a lot of people are. I know the national labs are.
Yeah,
It's like the national labs. If you're doing this, you're golden. Punched your ticket. So they probably the chemical companies in the same way. Basically, it looks like if you know a little bit of this, you can really impress your boss. Like if you figure out, it's probably worth spending a couple hours. I mean, it depends how easily you get bored. Like take the extrusion one and like figure out exactly really how they did it and reproduce it. And then I think if you do that, then you could probably do a lot of other stuff, because that's just a data set. It's like just any junk data set that you happen to have. And they just data mined it. So they didn't do any measurements at all. And they're making predictions from that. So you do the same thing with a company. You don't need a lab. You just kind of like data mine whatever you can get and then figure out how to turn it 1 to 0, 0 to 1, and like, and you just feed it into a web page algorithm.
Like you're a boss, you don't really need that to be like the analytics. You just say like here's the Excel sheets, like where we get the data from the team.
Yeah.
And they try that.
Yeah. Yeah.
Give us a linear thing, and it's like, all right, well.
Yeah, I mean, you're going to run into a lot of old people that are really opposed to this,
Yeah.
And then there's a lot of young people that are going to be eager for it. And the guy with the money is going to be absolutely for this,
Right.
Because he doesn't know what's going on at all, So, I mean, maybe a little bit. But he's eager to have something that can just like push the stock price up. That's it.
You like to mention machine learning.
Yeah. I mean, that's right. Like if you basically, because no one knows what it is really. And it actually, it isn't that.
Don't worry
Yeah, it's a lot of words in it, so it's just a lexicon you have to pick up, but it isn't that difficult. I mean, neural network sounds like a crazy thing, but it's just like a weighting thing where you're stacking up the weighting.
Yeah.
You have to figure out how many layers and then do a thing and iterate until it gets the right weightings, and then like boom, you can predict whatever it is you started with these two numbers.
I remember when I took linear algebra in freshman year, my first semester here, and he's like, my professor was talking all about this kind of stuff and then all about crypto before I was really got big.
Yeah.
And then he left the semester after. And like out here was like a very large company to like.
Yeah. Yeah.
Wow, like 2019, he was already getting up like busy.
Yeah, like this business analytics thing, they have, if you look at, they have like 50 companies that are paying to run that thing, and basically they're just training kind of like a couple of years. And then those people all immediately snatched up, like there's a lot of money in it. But I mean, it looks like it's going to be pretty boring, but like cornflakes and like what color is the package, and
Yeah,
that's the kind of thing, right? So how's that going to affect the stock price? I mean, it's like, so, is it cold outside? Is there a rainstorm coming? We put all the data from the Internet of Things, every possible thing into the cornflakes price. Then like you can figure it out down to like whatever. And like what are the parameters that are important? Everything's kind of the same if you look at it that way. So anyway, so I got Friday, I'll go through, there's another paper in dielectrics. And then I put up the finals, like 2 questions, 2 papers, and the papers are up there. So like you don't need to do it, but everyone else has to do at least one of them, And then Friday, I guess Thursday of finals week next week, that's when it would be due. But that's the last final day. And then anyway, so that's about it. So all right, put there.